Hi there, my name is Charles Suwaswani Msipa. I'm your e-tutor for Calculus A, MAT15121. Welcome to this presentation on Introduction to Limits. Limits constitute a very central concept for your later studies of mathematics. So during this presentation, or at the end of this presentation, I would like you to be very clear of concepts like when we say something is defined. In this case, we're talking in terms of values of a mathematical function, or when we say a function is undefined or a value is undefined. We also need to understand what we mean by a right-hand limit, left-hand limit, and at the end we need to be able to read this kind of an expression and be able to understand it fully. Just briefly talking about these two, remember we are dealing with real numbers, and our very accurate picture of real numbers is what we call a number line. In this case, let's look at the x-axis, and we've got the reference point 0. Now, if we pick any number a, like we have here a, you must notice that we can approach this number, or we can come to this number from only two directions, and the directions are coming from the right or coming from the left. That should help you to later understand what you mean by right-hand limit or left-hand limit. Now, coming to something like defined, the concept of defined as opposite to undefined, we should understand, like if we say x is equal to 2 or x is equal to 3, here we're talking about a definite number. We know exactly what we mean. But in some calculations, sometimes we come across some calculations which delivers expressions of this form, 0 over 0. But we know that we're never allowed to divide by 0. And then this kind of an entity, which frequently appears in mathematics, is an undefined entity. Similarly, we can have something like a over 0, and this also undefined. And you can also have an undefined entity of the form infinity over infinity. But be careful here, infinity itself is not a number, it's just an idea of expressing some idea of being bigger than what we can handle or manipulate as a number. So actually it's quite a tricky idea to talk about infinity. If we put like natural numbers like 1, 2, 3, we know that this sequence of numbers or this queue of numbers does not stop. Then we can just say it grows towards infinity, and infinity is not a point or a number which we can get to. So to express that the idea of not terminating, we can use infinity. Now let's proceed towards the concept of a limit. First of all, we know that if we've got a function, let's say we've got a function here like y is equals to f of x. Now, we know that x, we call it our independent variable, and the y is our dependent variable, by which we mean that to get the value of y, we should freely choose x, hence we say independent. And then once we've chosen x freely, we then calculate y. So y becomes dependent on x. Dependent. dependent on x, and x is an independent variable. Variable meaning it freely changes values, in this case along the real number line. So looking at this graph, like we've got a point here, we should always understand that this point being on the graph of y here, that point we have got x, comma, f of x, in this case f of x representing our y coordinate on the vertical axis, and the x chosen from the horizontal coordinate, the horizontal axis, and the y there on the vertical axis. So everywhere we see a point on the curve, that point will be of this nature: x, the independent variable, and the value of the function at x. So if we join those points, that's where we get this graph. That is very important to understand. Now, coming to the idea of what we call a limit of a function, let's look at this table, which is in your study guide. We're given a function here, which is x squared. Let's try to separate there. The function is f of x equals to x squared minus 4 over x minus 2. Now, if we were to sit down and try to evaluate this function so that we can get the points on the graph, the functions graphs there, we can see that if we get to evaluate the function at 2, we'll get 2 squared minus 4 over 2 minus 2, which will give us 0 over 0. Now, like we've said, this is an undefined entity. It cannot be taken as a value of the function. In this case, in drawing this graph, we must actually leave a kind of a window here, which I'm magnifying just for visibility. But once we've got such kind of a situation, or observe that in an expression we've got such kind of situation, we then wonder what happens as we approach problematic point 2, approaching it from the left or from the right. Now, the analysis of that behavior of the values of y as we approach this problematic point, which is x equal to 2, is what takes us to what you can call the limiting process. Limiting process. Now, we're starting here with values of x, 1,9 followed by 1,99, which is actually bigger than 1,9, and we follow with another number which is bigger than the previous 2, and up to 1,999. Now, if we evaluate that function, as you can see, we haven't here touched 2 because 2 is our problematic point. Now, when we evaluate this expression, we see that the values of y, or the values of x are increasing bit by bit towards 4. As you can see here, 3,9 is close to 4, but it's not as close as 3,99, and 3,999 is even bigger than 3,99, which means it's closer to 4. So which means as we evaluate and approaching 2 here, these values will be approaching 4. Now, to say that or express that mathematically, would write then limit as x is approaching 2, and a minus there means from the left. This minus here means we're approaching 2 from the left. In other words, we are moving towards 2 in this direction. Then, since we observe that these values approach 4, then we say limit of f as we approach 2 from the left is equal to 4. And this is now what we're going to call a left hand side limit. Now, once we're satisfied with the behavior of the function as we approach x is equal to 2 from the left, we also do similar analysis from the right. Then this is what happens. You've got 2.1, and we want a number which is less than this one. We get 2.01, and then the next one 2.001, and in this case, what these numbers are decreasing from the right towards 2. Now, if we evaluate them in that same order, we get these values, and as you can see, this number, this sequence here is also decreasing towards 4. In other words, the values are above 4, but they are decreasing towards 4 then. Then to express that, we write limit of f of x. Now, in this case, of f of x is this line. As x is approaching 2, but 2 with a plus there, then this plus again, it means from the right. Now it's approaching 2 from the right. And now our expression here, in this case, is talking about the right hand side limit. Now, when we've got such a situation where the right hand side limit here we can see is 4, and the left hand side limit there is 4, then we can write a statement which said, in this case, limit as x is approaching 2 from the left, that is limit of f of x, is equal to the limit of f of x as x is approaching 2 from the right is equals to 4. This situation happens with certain functions but does not happen always. And then when it, sorry, I wrote a 2 there, this is supposed to be 4. That was a slip of a pen. Now when the limit from the left and limit from the right coincide, then we say the limit of the function f of x exists. When would you say does not exist? We will say the limit of f of x does not exist when the limit of f of x as x is approaching a, in this case I'm talking about any number a on the real number line, is different from the limit of f of x as x is approaching a from the right. Then in this case here we say the limit does not exist. Now, in the case that we have here that limit exists, then to express this statement in a more compact or portable way is to say, we write here that limit of f of x as x is approaching 2 is equals to 4. In other words, now what we're doing is we're writing, after you have discovered that these size limits exist and they're equal, then we'll say the limit of the function f of x at 2 exists, and we write that statement this way. Then we say the limit of f of x as x equals it is turning to 2 is equal to 0. And here it's very important to notice that we don't get to 2. In our words here, we can emphasize that x is actually different from 2. What we're doing here, we're analyzing the behavior of the function or the values of the function as x is approaching, not as x is equal. We're just looking at as it's approaching. So it's important to, even if we don't write, it's important to have it in the back of our mind that x is not equals to 2. Now to look at another example which will give us what we've just said here, let's look at this type of a function. We're given a function here, g of x, which is equal to x squared minus 5 over x minus 2, or we can simply say y is equal to x squared minus 5 over x minus 2. Now, if we do this similar process of approaching 2 using a similar sequence used before and evaluating this function, we can see that the values of the function when approaching x from the left, the values of the function are increasing and increasing very rapidly. From 1.9 is 13.9, but when you get to 1.99 is 103.99, which in this case the function increases very rapidly this way. And in this case we're approaching 2 from the left, and a line like this one, which is dotted here, from our previous experience we know that this is the line we call a vertical asymptote. So now if we want to express that process of time here, we would write it this way as limit of g of x as x is approaching 2 from the left, and rounding off this value to 3 decimal places, we've got it as 10,004. Now if we come now and approach 2 from the right, we'll be coming from this direction, approaching 2, which is the number here, 2. What we have 2.1, then we decrease that to 2.01, 2.001, 2.001. You must observe that this is decreasing towards 2 on the lumbar line, is coming from the right towards 2, which is here. And evaluating that, we see the first value we've got here is minus 5.1, which is somewhere there. But immediately when we move, we decrease that to 0.01, we get minus 95.99, which is far below minus 10, somewhere there. And then looking at this process, we see that up to its value, rounding this to 3 decimal places, we've got this a limit of g of x going to going to 2 from the right is equals to minus 9.99. In this case, that's where we've got the limit, in this case, of g of x as x is approaching 2 from the left is equals to 10,004, which is not equals to minus 9.996, which is the limit of g of x as x is approaching the same number 2 but from the right. Now when we've got this kind of situation, that's when we're going to say, therefore the limit of g of x as x approaches 2 does not exist. So the idea we're expressing here is that when a limit exists, the side limits must agree. Now the limit from the right and limit as you approach from the left must agree, and that value must be unique. Like we know when we evaluate a function at a point, we must get a unique value that is similar to a limit. When a function has got a limit at a point, that value must be unique. Like that was must be one and the only one. So I hope at this point you understand what do you mean by existence of a limit. Now I would encourage you to go further study your study guides and your textbook and try to see if you consolidate the understanding of this concept and try to do some examples. Our next discussion will be discussing some manipulations we do mathematically to calculate limits, because this type of analysis we've done here is not always economic in terms of time and paper to write on. So we need to find analytic methods of trying to determine limits of functions without necessarily going through the tables of values, because sometimes we might not even have calculators or even power to supply our calculators in order to calculate this. So good luck. Meet you in the next discussion, and thank you for listening.